Okay, so the main topic of today's lecture is mixed Hodge theory. So the starting point of this is a wonderful discovery of Deligne that if you have a general variety, say X over C, then its cohomology is an iterated, in general, extension of Hodge structures of different weights. Which was first explained in his paper in, I think, the Nice ICM, called Terry de Hodge 1, which is a very short paper, and the only thing that, well, I wish people would write short papers as short as that these days. Okay, so the name of the game here is filtrations. So just to fix ideas, filtrations, which will, for this talk, will always be finite. So we just mean that we have V is some object of an abelian category. And then we have increasing and decreasing filtrations. So we have a decreasing filtration is just a decreasing sequence of objects, of sub-objects, Fn of V. So this is decreasing, so we've got that way round. Such that for some sufficiently large n, f upper n of V is 0, and f upper minus n of V is the whole of V. And then increasing filtrations, we just write the index at the bottom. So we have Gn, say, so it'll be Gn V now is contained in Gn plus 1V, etc. And then one has the associated graded objects, which we have to be careful how we write them. So this is Fn modulo Fn plus 1, and for an increasing filtration we do it this way around, and it's Gn modulo Gn minus 1. And obviously you can just pass from one to the other by changing the sign of the indices. So then you have an equivalent definition of a Hodge structure of say a pure, say a Z Hodge structure, or from last time we had, so this is weight n. So we still have the underlying Z module, and then instead of having a bigrading, you have a filtration on HC such that for all P, HC is the direct sum of FP, and Fn, what do I want this to be? N minus P plus 1. So if we just draw the picture here, P minus 1, Q plus 1, and so on, P plus 1, Q minus 1, and so on. So this is Fp, and then this is F bar Q plus 1, and so that's F bar N minus P plus 1, if P plus Q is N. So that's a nice way of, and so you recover the other definition with the by grading HPQ as just FP intersect FQ bar. And these are, so in Deline's terminology, the filtration F and the filtration F bar are opposed, which means that they sort of overlap in this rather natural way. Okay, and then we can define what a mixed Hodge structure is. So let's do it for Z, and we can also Z mixed Hodge structure, or no, you can have an A mixed Hodge structure for A could be Z or Q or R, but for the moment we'll just do Z. So there's a mixed Hodge structure. I've used that already. Is, so it's a triple H consisting of, again we're going to have a finally generated Z module HZ, and then now, well, that'll actually be 3 filtrations. So HZ is a finitely generated Z module, and W is an increasing filtration, the so-called the weight filtration. On, so this is rationally defined. And then F is a decreasing complex filtration. This is the Hodge filtration, just as before. On the complexification, I'm sorry? A? And where's are there some other A's? Here. That's article. Okay, I'll write in sort of Russian English just for a moment. That's it. All right. Okay, yes. Yeah, for me too.
Why you're erasing that is the B's over there don't belong.
Which B's?
The definition of Hodge structure, FPV is the
Oh, I see. Yes, I've got. Yeah, this is FP of or FP of H. Yeah, it should be H's. Right. Okay, so we now actually have 3 filtrations because we've also got F bar, and these 3 filtrations interact in a particular way. So such that on the graded, for the weight filtration, so on the nth graded, for the the filtration F bar induces, so there's an obvious filtration you get on the graded just by taking the intersection with the numerator and the denominator. So that induces a pure Hodge structure of weight n. Okay, maybe it's worth doing a little picture here as well then. So if I look at the sort of graded nth piece here, the weight filtration. So this is pretty schematic. So again, if I've got PQ where P plus Q is n, P minus Q1, Q plus 1, and I'll write the weight filtration going upwards. So this will be n minus 1. Will be along here. So we'll have here P Q minus 1 and so on. So here are the various the PQ parts of the individual graded things. So no, do I want to draw it like that? Okay, I always get... This was probably a bad idea. It was probably a bad idea because I didn't plan to do this. But let's see. Let's not write that down at the moment yet. Okay, let's label the dots in a moment. Hold on. Right. So this is P plus 1, Q minus 1. And now, let's just check out. Let's see. So, okay. So this side here is going to be FP. That's everything to the left of here. So that means that this should be P comma Q minus 1. And then to the right here is F Q bar. So this is P minus 1 Q. Okay, so and then here, we can downwards here is W N. So these three filtrations sort of intersect at some point in this thing here. Now, it's perhaps worth mentioning that three filtrations is much more complicated than two filtrations, just from the point of view of linear algebra. If you have two filtrations, let's call them on a vector space V, say let's call them F and G, then it's not hard to show. It's basically Zassenhaus's lemma says that you can find a direct sum decomposition of V such that Fp is the sum of the things V P prime Q, where P prime is greater than or equal to P and Q is anything, and GQ is the same thing where we allow P to be anything and Q prime to be anything, to greater than or equal to Q. So you can split the filtration by subspaces non-canonically. On the other hand, if you have three filtrations, this is false. This is false because, for example, if you consider filtration F, G, and H given by say F naught equals G naught equals H naught equals V, which let's say is C squared, and then F1, G1, H1 are just three different distinct lines in C2, and then the F2, etc., all 0, then you rapidly convince yourself that this is impossible, just because the dimension of the space is not divisible by 3. So 3 filtrations in general are rather, this is quite a complicated linear algebra gadget. And in particular, it has some continuous moduli, which these things here, which these don't. I mean, here it's just given by this. At least if you just work over the complex numbers, just the filtration data is just given by numbers, whereas here it's given by some other things.
What do you mean by equal? This equality.
This equality here.
Yeah, I mean the meaning of this. How these.
Okay. What do we mean by? Okay. So yes. So the point is that H is a Z lattice, and so this doesn't mean the conjugation of this space. It means the. I shouldn't put the bar over there. I should just put it over the filtration. So, perhaps, so for the rational, or if you like real structure on H, you can conjugate this, take the complex conjugate of this subspace and get another subspace.
Surely this line is the bar of the C. You haven't defined a thing called that bar. That is the definition.
I bet that is the definition. Yes. Yes. You've got a real vector space, and you've got a subspace of the complexification, so you can take it.
So you identify this twist with a subspace. No, it's a subspace.
Well, so.
It's a subspace. There's no identification. It's also what it's equal.
Yes.
The subspace is the disjoint with direct transposable. No, it's not.
But I think I know what your question is. Your question is that this space is normally not the same as this. But these are the same. Yeah, said theoretically.
It's the same actual set.
Yes.
They're the same ones. It's the same thing. But what's the point of, you write it as the direct sum, but you...
Yeah, it's an internal direct sum of subspaces. And so let's just take a rational basis for HQ. This is given by some generators, and this is given by the complex conjugate of the generators. Yeah, but it's not complicated.
I need to understand the naturality. Never mind.
Okay, well, let's continue. And okay, so then there are two nice theorems. One is abstract theory, both due to Deligne. So we take the category of mixed Hodge structures. Now I have to say what the morphisms are. So the morphisms are just, say, morphisms of the corresponding underlying Z modules such that f of the Fn of H is contained in Fn of H prime, and the same with the weight filtration, Wn of HQ. So it just preserves the filtrations in the weakest possible sense. Okay, that's clearly an additive category, and this is actually abelian, which is not at all obvious. And then the other theorem is also by Deligne, is that if X is any complex variety, okay, any reduced scheme of finite type over C, then the cohomology of X has a natural mixed Hodge structure. And that in the case when X is projective and smooth, this agrees with the pure Hodge structure coming from classical Hodge theory. And this natural is actually functorial and enjoys many nice properties. Okay, now I don't actually want to describe this at all. It uses the theory of logarithmic singularities, and it's very well documented in a number of places. So the original treatment was in the various papers by Deligne, Terry de Hodge 1 to 3. So the proof that this is a mixed Hodge structure that's given there uses quite a lot of homological algebra. So very beautiful but quite subtle homological algebra involving filtrations and how filtrations on complexes interact. There's also at least in the smooth case, there's an analytic proof, meaning it uses like an epsilon more analysis and much less homological algebra. So that can be found in a paper by Griffiths and Schmidt. Which appeared in some conference. I'm not sure if there are any more than one paper than Griffiths and Schmidt. It's called Recent Advances in Hodge Theory, I think, or Recent Advances in this, something like in Hodge Theory, or I think it's called Recent Advances in Hodge Theory. Okay, so I don't want to discuss that, but I do want to discuss this abelian category a little bit, because that's a motivation for introducing Deligne cohomology. So let me do that now. So we've got this abelian category. Let's call it MHS. Is the abelian category of mixed Hodge structures. So we can ask, what are the, okay, well, the Hom groups, they're fine. So you can ask, what are the higher derived ones? What are the X groups? And I'll just restrict myself to looking at the X groups for where one of the ones is the trivial thing. But let me first say that if you have a pure Hodge structure, H of weight n, then if you set Wn of HQ to be HQ W n minus 1, HQ to be 0, this is then a mixed Hodge structure with just one weight. So pure Hodge structures are particular cases of mixed ones. So in particular, you have a Hodge structure ZR. Okay, so what's the HOM in the category of mixed Hodge structures? Let's just do it from Z0 to an arbitrary mixed Hodge structure H. Well, that's just the maps from Z to H of Z, such that f of 1, well, tensored with 1, I guess, is in W0, and it's also in F0. So if H is pure weight n, then this is equal to, so this thing is equal to it's not hard to see, therefore, that if this is pure weight n, this is 0, or rather, it's not 0, it's the torsion subgroup. If n is not 0, and if n is 0, it's just the set of elements of Hz such that H C tensor 1 is in what's automatically going to be in W0 because n is 0. It's going to be in F0, so it's also going to be in F0 bar, so that means it's in H0, 0. So this is just the 0, 0 integral classes, if you like. Okay, so for the X, there's something called Carlson's formula. So it's easiest to write this down if the weight is, if there are no things of weight strictly greater than 1. So the formula says that the Ext of the trivial Hodge structure by H is given by the co-kernel of this map. Which I'll call let's give this a name. Let's call this alpha sub H. And this is just the map given by x, y goes to x tensor 1. It's just the difference between the two obvious maps from into H.
And how do you define the X to have enough injectors or projectors?
You need X. It's an abelian category. It's just a set of 1 extensions.
Higher ones you need to talk about projectors.
No, you can have higher unit X. In fact, this is the X2s are more or less trivial. So in fact, you can also, okay, so I'll also say that XP MHS of Z0 H, like R, maybe not P, is 0 for R greater than 1. So there are some X2s, but to have X2s, you have to have torsion in here. And the X2s are sort of basically group theoretic X1s. So notice also that the kernel of this map alpha H is just the HOM, by what we just said there.
Another question about that, I mean, studying theorem about this next Hodge structure. I wonder whether if X is smooth, then F coincides with Hodge.
Yes, if F is smooth and projective, if X is smooth and projective, this coincides with the Hodge structure coming from classical Hodge theory from the what I mentioned in the last lecture.
So if it's not smooth, I wonder whether it's Hodge completed with the right around, F, filtration F. I mean, you have smooth one and you left can extension to. Well, at least for affine cases. I mean, you have a polynomial and you have filtration, and then you left can extension this on the
maybe we should discuss this afterwards, because okay, so let me just give some indication why this is the case. Let's consider, okay, so X1 classifies extensions. So let's suppose we've got an extension here. So how would you tell whether this extension was trivial? The first thing you could do is you could look at the extension of just the underlying Z modules, and then we could lift 1 to some element, let's call it E sub Z, in here. And now the other thing we could do is we could look at the so this is just F0 of Z0. Now this sequence is actually exact. This is not completely obvious. This is a consequence of the proof of Deline's theorem, which says that in fact these maps on the filtrations behave even better than this. Anyway, so this is actually exact, which is not obvious from the definition of morphisms. So we could take 1 here, and we could therefore attempt to lift it to some, let's say, EC inside here. And now if we can do that in such that these are actually the same, then we get a splitting of this extension of Hodge structures. So if these are both the same, you get that. In general, we can look at the difference. So since they both map to 1 here, so the difference EZ minus, or EZ tensor 1 minus E sub C is well defined modulo HZ here and F0 here. So it's a well-defined element of the co-kernel, and it's 0 if and only if this extension is split. So that certainly suggests that we're on the right track here. Okay, if you remove the condition that the wave filtration, what W0 is the whole thing, then you have to make this a little bit more complicated by fitting the wave filtration in as well. And I won't draw the picture there, but one can do that. Okay, one of these rubbers. Did I switch this on? Yeah, I don't know why the red light is not on. But nobody's complaining that it's not on. It's fine. Good. No, no, no. The X groups are always 0 above 2, and X2 is, in fact, always finite. In fact, if you ignore torsion, this is worth saying. Okay, so it's
On the board you wrote that it's 0 for r bigger than 1.
r bigger than. Yes, but that's because we got z0 there. If you take the x between two arbitrary ones, then you could have an x2.
Oh, you're saying x2 for everything.
Yes. Okay, I mean, it's like abelian groups. If you take abelian groups, the x1, z, any abelian group is 0 because z is projective as an abelian group. But x1 between two arbitrary abelian groups can be non-trivial. So it's worth saying that if you ignore torsion, in other words, i.e. in the category of Q-mixed Hodge structures, so where you have vector spaces rather than Z modules, then, so you get then X1 of Q0 by H is the same as X1 of Q0 by W0 of H. The reason for that is the weight filtration is increasing, and so if you had something, an extension like this extension E here, in which H, all the weights at H were strictly positive, then the weight filtration itself would just split that extension. Okay, so now I want to define Deligne cohomology. And the reason for this diversion into homological algebra that I've just done is that the sort of naive definition of Deligne cohomology in some sense makes absolutely no sense at all. I mean, it makes perfect mathematical sense, but there's no reason why you do what you do. So the idea is to motivate this definition. Okay, so let's suppose now we have X, which is smooth and projective. Over C, well, we work in the classical topology. So I won't bother to write all these X ands everywhere. Then we have the cohomology with Z coefficients, which maps injectively mod torsion to the cohomology with complex coefficients. And we saw last time, this is just the same as the hypercohomology of the complex, the holomorphic de Rham complex. And inside there, we've got the pth step in the Hodge filtration, and that, by the Hodge theorem, is the hypercohomology of this truncated complex, Fp, where we recall that this is just the thing that starts at omega p. So one way to motivate Deligne cohomology is what you want to do is just take Carlson's formula, which says that the Hom and the Ext are the co-kernel and kernel of this map here, and just derive it. So let's just sort of derive Carlson's formula. So this is the definition of Deligne cohomology. For H sub D and so how do we do that? So we'll just take the this thing here and we'll just copy this here in the following way. Okay, so we're just going to write down a complex. So what we do is we just take ZP, and then we'll take FP of the holomorphic de Rham complex, and then we'll map this by the same map alpha, which is just the difference map, therefore x minus y, into here. Okay, so this is now a complex. This is a complex. So we take the usual way people write this is to take the cone and shift it. We just take the total complex associated to that. Well, so this is a map between two complexes, so it's a double complex, right? And so I make so what is this total complex? I'll just write it down. Let's just write it down. So this total complex, okay, there are issues of sign, which we will ignore, but of course which one does have to get right. So what does this look? So we've got ZP mapping to omega, so let's ignore this for the moment. So the total complex of the map from ZP to this is just the slightly longer complex by doing this, omega 1 and so on. And here we have an omega p minus 1, omega p, and then we carry on. Okay, so that's... I haven't finished yet. This is not the total complex. So that would be just the total complex if we didn't have this in here. It's just the trick that just got by concatenating the ZP and that. Now if we want to put this in, so that means we have an FP, and this is degree 0. Omega p minus 1 is in degree p. So we also have to stick this complex in. So that's plus 0 here, plus 0 here. And then here we have plus an omega p. Here we have plus an omega p plus 1. And then here we have d, except probably there's a sign here. So and this is, I guess this has to be minus 1 for it to be a complex. Okay, so that's just the simple complex associated with this double complex. Or it's, if you like, the mapping fiber or the shifted mapping cone with some issues about signs which we will just ignore. So, of course, this thing maps isomorphically to here. So that has the same cohomology. So it's quasi-isomorphic, has the same cohomology as just this much easier complex in which you take ZP, and then you go to O, and you go to omega 1, and then you go up to omega p minus 1, and then you stop. So the classical definition of Deligne cohomology is you just write down this complex, you just pull it out of nowhere, and you say that's what it is. But where it really comes from is it comes from this Carlson formula for the X groups. Okay, now let's look at this. So,
But now it's ordinary form.
sorry?
This is now. Even if you take the total complex.
Yeah. Well, it's a complex, so you have to take hypercosmology. Yes. So maybe just to no, I won't do that yet. So first, let's. Okay, so now let's look at the map between this complex and this complex. So that will give us a long exact sequence in cohomology. We get a long exact sequence. So let's have the Hn Deligne cohomology. So that will map to, just by forgetting about this, so mapping this to 0, to the cohomology of this, which is just the sum of Hn of x with Zp coefficients plus the cohomology of this, which is just the Fp of the Hn with complex coefficients. And then that continues, mapping into the Hn of x with complex coefficients and so on. And here we have the same thing here. We're going to have the Hn minus 1. And mapping into here, we have the direct sum. And this map is, okay, it's just the map alpha of Hn of x. And likewise, this is just alpha n minus 1. Sorry, no, this is alpha of Hn minus 1 of x. So this breaks up into short exact sequences, where here we have the kernel, and here we have the co-kernel. So we get naught goes to the co-kernel of alpha of Hn minus 1, goes to the Deligne cohomology. And this is alpha with a p, of course. I should put the p there. We've got this twist, twisted by p. And here we've got to the kernel of alpha Hn. Now, as we saw up here, Carlson's formula tells us that these are just, at least if the weight here is, so if, well, there'll be two ifs in each case. So here, this is equal just to the Hom. I'll just write it this way, of Z minus P into Hn if n, let's get my numbers right, 2n, n. So that's to make the weight of this be less than or equal to 0. We want 2p to be greater than or equal to n. And here we want, this will be the x1. That's the same thing. Well, let's write it z minus p by Hn minus 1x, and that's if n minus 1 is less than or equal to 2p. And we're only going to be interested in cases where this holds anyway. So what is this? So we saw before, this is just the torsion if n is not equal to 2p. And if n equals 2p, it's just the pp classes in H2p. So isomorphic, maybe I should write there. If n equals 2p. Okay, and I'll come back to this in a moment. Okay. That comes from the condition that W0HQ equals HQ. So this Carlson's formula holds when the weight of H is, the weights are less than or equal to 0, and the weight of Hn twisted by P is n minus 2p. Okay, so this seems kind of a bit abstract. So let's just write down what happens when p equals 1. Well, then this complex here, okay, so we've just got, we stop at, it's just, so the complex is just, always quasi-isomorphic to the complex Z1 mapping to OX and this is just the inclusion map, and so this is just isomorphic by exponential to the complex which is OX star in degree 1. This is what one writes as OX star minus 1. So the Deligne cohomology in particular so H1 in particular Deligne and also H2 Deligne with coefficients of Z1 is just H1 of OX star, so that's just pick. And now we write down this exact sequence here, and n is 1 and p is 1, so both of those inequalities hold. And so we have, so n is 2, p is 1, so they still both hold. So we have pick x mapping to H2 x z. Okay, I'm just doing it. And here we have, on the left-hand side, we have the co-kernel of this alpha. And then with a, so that means you take, this is alpha for H1 with a 1 twist, and so that's just H1 xc modulo F1 modulo the integer coefficient. So this is just H01, which is just H1x OX modulo H1 Z1. So this is just the same as the exact sequence coming from the exponential sequence. So here we have the Picard group, here we have the discrete part, which is just the 1-1 classes in integral H2, and here we just have the Picard variety. So this is just Okay, so I'm running way over time, so I'm going to have to be extremely short now. So let me just talk for 5 minutes about what happens when p is greater than 1. So in particular, the pick is just equal to, yes. So we have this equality here. So in particular, we have a cycle class map, which is just the identity map from pick to there. Okay, so then there is a cycle class map, which I won't define. Well, CLD, let's write in a diagram here. So it will be from the Chow group of codimension p cycles to H2p delene with coefficients in ZP. And now we have the map to this Hom here, which is just to the, so we have a map integral PP classes. And this composite map is just the cycle class, integral cycle class map that we had in the last lecture. And so inside here, we have things which are Z homologically equivalent to 0. I'm being a little careful here because some people are rather, when they write, a bit vague about when they write homologically equivalent to 0 meaning Z homologically or Q homologically. So I'm going to distinguish between that. And then here we have this kernel, which is this X1 group. This X1 group so this is just H2p minus 1 with complex coefficients modulo the p part of the Hodge filtration and modulo the image of the, well, modulo, let's vary like this, the integer cohomology modulo torsion, obviously. And this group is called JP of X. This is Griffith's intermediate Jacobian. And this map here, which you get it because that's composite is 0. Here, this is the Arbel Jacobi map, higher Arbel Jacobi map. Now, of course, because H2 delete with coefficients Z1 is actually pick, your immediate reaction is that, oh, this is wonderful, because now I've got some transcendental interpretation of the Chow group in terms of this. But this is completely false. This map is in general neither injective nor surjective. So it can have a huge kernel, and it can also have a co-kernel. So let's just say, unfortunately, CLD is far from being an isomorphism. In general. For 0 cycles, this map is just the Albanese map, and Mumford shows that the Albanese kernel can be huge. If I had another half hour, I would say more than that. So I won't say really any more about that. one role of this intermediate Jacobian is that Griffiths used it to prove the fact that algebraic equivalence and Tor equivalence are in general different. But I have no time to say anything about that, so I just want to say two remarks before somebody rings the bell at me. Both of which probably are related to the next lecture. No, okay, I've got three remarks. First of all, you can define these Deligne cohomology groups for any x. I just did it for smooth projective ones because that's the one for which it's easiest to write down the Hodge structure. But if you use Deligne's recipe for mixed Hodge structure, you can do these in the same way for any x. And then, of course, the group on the right here, in principle, is more complicated because the cohomology can have more than one weight. That's the first remark. So here we were considering the case when n was 2p. But if n is not 2p, then you have higher cycle class maps into Hn Deligne x zp, and these come from, if you like, from motivic cohomology. Hn motivic p, which is just either these higher Chow groups. See if I can get my, I think it's 2p minus n. And then the third thing is that we can also look at other coefficients. And now there's something that's not so completely, well, the first guess is wrong here. So this is the Hn, and now we take the total complex, except we replace Z by A, so we have AP plus Fp of omega dot going to omega dot. So this is not the same, so it's not equal to, it's not just obtained by extending coefficients, because you've got a continuous part in this group as well as a discrete part, and the continuous part, of course, you just have to write it down separately. And in particular, you have the ones when A equals R, and then the maps in 2 are the high regulator maps, which already occurred in Francis's talk, and will occur, I believe, in Matthias's next talk. Okay, and I can ring the bell. Yes. Okay, so there is, of course, polarization, and I've deliberately ignored discussing polarization at all. But yes, it does play some part. So if you use polarized Hodge structures, okay, so then the point is that if you take the pure Hodge structures, then if the polarized pure Hodge structures are semi-simple, like ignoring torsion. And so the formula for when H is of weight 0 in the polarized case is different. But in the non-polar, since the polarization on the mixed Hodge structure is just, by definition, a polarization on the graded pieces, it makes basically no difference. Yeah, well, I mean, those are the ones you're going to use. I mean, it's even possible to define this with C coefficients. When you define it with C coefficients, you just have to regard F bar as just being a completely different filtration. The definition is slightly different because you have to put F bar into the picture somewhere, but it's not it's no big deal. With torsion coefficients, you just get I don't think it's very interesting. You could, I mean, you can define it. Well, you can't define this with torsion coefficients. Because A has to be a subring of. Yeah, I mean, the only thing you could do is you could just take this and map it somewhere to 0. I mean, Hodge structures which are torsion are basically just abelian groups. So mixed Hodge structures which are torsion just abelian. So there's really nothing there. Oh, yeah, sure, of course. Yeah, you could do, yes, you could write, yeah. So, I mean, you could write down a cohomological interpretation of the torsion, just by doing the sort of the obvious thing, write down the complex, write down the multiplication by n map, and blah, blah, blah. Yeah. But I think you're just going to get ordinary cohomology with torsion coefficients out of